Hi folks, welcome to Holroyd 255. Holroyd 255 is our laboratory where we do all kinds of cool stuff. Is our laboratory where we do our physics stuff, our measurement stuff for ISBT112. It's also the laboratory that we use for our instrumentation and measurement class, where we do a whole bunch of interfacing, so much of stuff running around here. It's also where we do our laboratories for ISBT111, technology and systems analysis, a whole bunch of electronics in the spring. And also in the spring, we do a whole bunch of material analysis. Most notably, we use these, Tinius-Olson is the name of the company. These Tinius-Olson, there's two of them, there's twins. They are universal testing machines that allow us to squish things, bend things, and flex things. So I wish we were allowed to be in here for this semester, but that's not going to happen. So I'm going to try my best by giving you a tour of what's going on and give you a tour of what the experiment looks like and collect some data. And then we're going to spend a lot of time this semester concentrating on what the data means and get a real deep understanding of the equations and the models we're going to use. So in other years past, we would have sort of split the difference between the modeling and the being in the lab, but since that's not going to happen, we're going to concentrate on the modeling stuff. So you guys were really fantastically good at it. Obviously, I have my phone over here setting up to make sure I'm still recording. I don't want to talk for a long time and not record, so that's us. But where I want to start with our first activity here that sort of launches our measurement for the semester is back here, and hopefully this works out. We had mentioned, or I had mentioned, or we both talked about measuring processes this semester. Of course, that's what the darn course is called, Technology Foundations 1 Processes. And what we're going to be doing is just like sending an angry bird into a slingshot and having it crash into somewhere. We can think of a ping pong ball as, it's not an angry bird obviously, but it sure looks like one, especially if it's flying through the air. I don't know what this is going to look like on my GoPro, and I may not be good at it, but there you go. There's an angry bird flying through the air. Fantastic, and it's doing the lovely little tiny parabola go through. So we'd like to spend some time in the beginning of the semester here, sort of describing that. How can we tell somebody else, hey, if you take an angry bird the size of a ping pong ball, sure looks like a ping pong ball, and you were to chuck it at a certain angle and it were to fly from one hand to the other, what path would it take? And how long would it take to get there? How high would it be? And where would it be if we were to do all these? We want to understand the process, and that's what we're doing this semester. So one of the things that we would typically do in the lab, were we in the lab, is we would take this ping pong ball and we would do something with it. We'd have a process. Again, we could bounce it off of each other. We could bounce it off the floor, of course. But when you do get back in here, you'll notice that we have some tapes, some masking tape on the wall. There's a sort of a beige one over here. Maybe that's pink. There's some red. There's some green. And if you look closely, you'll notice that each of these pieces of tape, this is a meter stick, so it's 36 inches to a yard, but it is 0 to 99.91 over here. That's a meter. If I were to take two of these guys, one there and then one here, that's right about a meter or 2 meters up. And what we would do is we would look into finding out the time it takes for this ping pong ball to drop from a height of 2 meters down to the floor. Okay, so of course I could go ahead and do that. Ready, set, go. Down it goes, it bounces. Of course I wasn't using my watch. I could time it with my stopwatch. I could use my phone if it wasn't doing my GoPro. And we could measure that, and that's typically what we do in this lab without doing the thing we did a week ago when we were talking about measuring 5 seconds. We typically would measure this drop of this ping pong ball, and we'd use a smartwatch, or we would use a smartphone to make that measurement. There's a couple measurements we need to do. Obviously, we need to figure out how far is 2 meters. That works out pretty well. I had to use this twice, obviously. I could have used this this ruler stick. It also comes in, this is a 12-inch ruler stick, obviously, or a ruler, and On the other side is some millimeters and some centimeters. We could use that as well. So we could measure the distance. And then to measure the time, we could use our watch. And we'd go ahead and measure that. And of course, we'd get some uncertainty and we'd get some variations. And then we'd take the averages and figure it out. So what we want to do is we want to do this a little more scientifically, if you will. We want to improve our ability to report a value with high accuracy and high precision, both of those. Accuracy, pop quiz, difference from the truth, and precision, measurements, what is their distance from each other. So we're instead of just doing this sort of me throwing a ping pong ball around and using some hands, there's nothing wrong with doing that. We're going to try to scientifically do this using some scientific equipment. So one of the pieces of equipment we have over here is it's a piece of aluminum, extruded aluminum. It's pretty big. It's not meant to be a ruler. It happens to have a ruler on it. And if you look really, really close, if I can see way up there, it's about 2.27 meters, 227 centimeters. And if I go ahead and use it to measure where that tape is in the wall, not only need one of these things, not two. And I know there's an error. I'm not that tall. It's right about two meters. That's fine. And of course, I could go grab the ping pong ball and drop it from there, and that's fine. That's wonderful. I could time it. But the difficulty is that this process of the ping pong ball falling down from 2 meters, while it's in the air, if we did this measurement, it's around 0.6 seconds. We have less than a second to get our measurements done. And if someone were to record where is it, it'd be kind of difficult, at least for human scale. And again, this up and down motion is kind of inconvenient because you always have to put the ping pong ball way up at the line. It has to drop down. It's free falling. It'd be great if we could pick a different process. So the different process we're going to look at is we're going to look at things that move, but instead of looking at the ping pong ball as it falls up and down, we're going to take this this piece of metal, this track, which is why it's made this way, and we're going to put it horizontally. And I know we all know what horizontal means. Vertical's up and down. Horizontal is like looking at the horizon of the ocean. That's why it's called the horizontal. That's why it's called the horizon. And what we can do then is we can roll the ping pong ball back and forth and maybe do a little bit more controlled. Maybe we don't have to push it as fast or push it as hard, and maybe we can measure it as it goes along this tape. I'm going to put this against the wall here, and chances are it will fall and crash. And it will scare the living crap out of me. Maybe we'll try that. But I'm going to go ahead and take my ping pong ball here and walk over to a second copy. We have a bunch of copies of these, of course, which is why we would have lab in here with multiple stations. We could indeed set this up. I now have it, quote-unquote, horizontal. I've put some feet on the bottom of the rail. This is what the feet look like. They're not very impressive. They also are out of aluminum. You can go ahead and you can adjust the feet to go ahead and make sure that it's level. We want it to be level. I didn't double check to see how level it was. I'm going to move this chair out of the way. Fantastic. But if I stick this ping pong ball there, it doesn't seem to roll either direction, so maybe it's level. And maybe we could go ahead and say 3, 2, 1, give it a shove, and it could go down and bounce off the end, and that's fine. It actually did pretty well, okay? But maybe in another area over there, maybe it goes side to side. We could turn this into a bowling game instead of an Angry Birds game. Again, if the process gets very, very complex, if I do crazy things like spin it, and that is difficult to replicate. It would be difficult to make that happen exactly the same time, multiple times, so that we could take multiple measurements and then average out the results. So we're going to retire the ping pong ball. Let's not do this. And I think you saw one over there. Instead of taking a ping pong ball, which is perfectly fine, we're going to use a little tiny cart. So this little tiny magnetic cart has a magnet in it. And one of the reasons why it has a magnet in it is so that I can refer to or bounce off of the magnets down here. So if I put these 1, 2, 3, 4, put these low friction wheels in the track, now when I give it a push, it doesn't wander down the track side to side because it's in these little tiny tracks, sort of like a train. And I go ahead and give it a shove. It bounces off the magnet. I was waiting for that to crash. Yeah, it does pretty well. It's a pretty strong magnet. I could play this all day. This is sort of like pushing it and having it fall back down. It sort of looks like a parabola. It looks like a parabola horizontally where it goes up, slows down, stops, and comes back down. And if I were to go ahead and plot that as a graph, it would be go down the track, stop, and then come back where it was. So it's a similar motion, but it's not ping pong balls falling down the wall, and it's definitely not this heavy little cart thing falling down the wall. So that's going to be our stand-in for describing this type of motion. We want to watch something move. We want to see a process of this thing fly down the track. That thing seems to be slowing down right now, but if I were to give it a little bigger shove, it's meant to not slow down. There's no way that we don't have this thing slowing down because these are not the world's greatest wheels. If you've had an air hockey table, you can use an air hockey table. Some setups, they fill this with dry ice and use the dry ice to provide a little cushion of air. But this is fine for us. We just want to roll this down the way here and let it bounce off if that happens to be one of the things we're going to study. I'm going to put this thing back. And we could do that, but what we can also do is instead of me giving it a shove, giving it a shove is fine. Again, we could go ahead and do this while it's on the rail. But we can also use another piece of equipment that gives things shoves, and that's this propeller. Oh, by the way, we use the English word propeller because it propels things along the way. I'm going to try not to cut my fingers off. I apologize if I cut my fingers off. This thing's pretty sharp. It's just a piece of wood. I've cut my fingers in here plenty of times. I just get a nasty smack. But if I turn this thing on, it gets loud, and you can't feel the air. It's pushing. That was stupid because I'm wearing my contacts. It pushes air this way. It's not a front of an airplane where it pulls that way. So if I go ahead and put this on here, and yes, the same company made the propeller as it made the little cart. If I were to turn this on and then let it go, it's going to start sailing, okay, and it's going to take off. So what we're going to do is we're going to use that motion as a stand-in for the ping pong ball starting at 2 meters, and then I'm holding on to it, obviously. I let it go, and then it slowly speeds up, keeps speeding up, keeps speeding up, keeps speeding up, and then it hits the ground, okay? So that's what this guy does. I hold it, and then I let it go. It speeds up, speeds up, speeds up, speeds up, until it crashes into something. But it's very repeatable, so we can do this measurement over and over and over again. And then if we take those measurements, even if they're not exact, we can average them, and then we can look at the average and see if we can get some statistics on them, the standard deviation, which we talked about with the spreadsheet before, all the fun stuff that we normally do inside of a laboratory. I'm going to go ahead and put this upside down because I know if I walk away, this is somehow going to magically turn on and shoot across the room, and I will be afraid. So over here I have a copy of what I just did. Here's this guy. And what I'm going to do is if I were to go ahead and turn this on, this guy's not as powerful. The batteries seem to be down a little bit, but it speeds up. And if I let it go, it'll crash into this thing and back and forth. I'm going to catch it before it crashes. But that's ultimately the motion that we're going to measure today. We're going to start somewhere down here on the number line, not the whole way back here. Somewhere in here, I think we'll find out what it says in here we should do. We're going to turn this on. I'm going to drop it, but because this guy is not pushing as hard as gravity was pulling down the ball over there, it's going to slow down the process, but it's still the same process. So we can measure where it is as the time moves on. But again, having a student or having me watch when it passes 150 and write that down, and then do it again and see when it passes 160 and write that down. That's one way to do it. It sounds like a lot of work. I'm not really into doing a lot of work. So it'd be great, since we already have sort of turned this into a physics problem, it'd be great if we could use a sensor to solve that. So this is what the sensor looks like if I could grab it. I didn't grab one over there. I'll grab it over here. I didn't have a copy of one. This is a sensor we're going to be using, and this is an ultrasonic sensor. I'm going to make sure this guy is set at 0 here. So what this sensor does, you can see it has a gold speaker inside of it. The fact that it's gold just means they chose to use gold. It's not because it's really, really expensive. But it's an ultrasonic sensor. What it does is it sends out a puff of air, a sound, and then it waits until that sound hits something and then comes back and then records the time. It records the time between heading out and heading back. So it is an echolocating machine. It's a sonar. It's the same way that a bat finds prey or where it's at in a dark cave, if you've studied bats before. It's electronic, so it needs to be plugged in. It needs to get power, and it needs to give it signal. So I unplugged it to show you what's going on. So I'm going to plug this thing back in again as a standard cable. You just saw it turn on. I'm going to attach it here. Yes, the same company that makes this rail, makes this ultrasonic sensor here. And oh, by the way, it happens to have a setting as far as being wide or narrow. I think you can see that guy right there. We're going to keep it on narrow. That depends on what it's going to see as it pulls down. That cord I just plugged in plugs into this interface box. It is powered on, and it has a yellow plug and a black plug. The yellow plug is the plug that sends out the power and causes this thing to make a snap. It really does sound like a snap. You'll be hearing it in a few seconds when we turn it on. I can make the snap once with my tongue, like that. It's sort of like tisking your tongue. And if I did it fast enough, it would sound like. That's just me sort of echolocating with my tongue, snapping my tongue. This does the same sound. It doesn't whine, or it doesn't sing, or it doesn't play a perfect tone. It just makes those little pops, and those little pops fly through the air. They smack into whatever it sees, and then it comes back. And then over here on the microphone side of things, there's a processor inside this box that communicates that distance of how long out and back, and then it echolocates what it is on the other side. So we're going to be using some software that does all of this for us. It's fantastic. I just want everybody to understand what we're measuring. So what we're going to be measuring is we're going to be measuring this echolocating machine. They call it the motion sensor. And the motion sensor is going to send out a pulse, several pulses, fast, and it's going to hit this and come back, and then it's going to be able to determine where this thing is. So if we were to measure it right now, it would say 127 millimeters, or 12. Well, that's not 127 centimeters. That's way too small. Or 1.27 meters is where that's sitting right now. It's going to completely automate this and then allow us to take the data and look into it. Okay, so let's go ahead and see if we can't fire this thing up and make it work. I'm totally blind, just like a bat, so I should echolocate. I'm going to grab my little reading glasses here, my little spectacles, and put them on. I have printed out our